Now it's time to talk about why Diffie-Hellman key exchange is considered secure, because this is it's not obvious to me that it is. Um, it turns out that it is, but there are some delicate mathematical issues that come up that we need to talk about. I really need you to do what you can to focus really hard on this lecture because these issues that come up in this lecture, this won't be the last time that we see them. These are going to be some of the same root issues that make El-Gamal and RSA safe encryption schemes. So let's talk about why is Diffie-Hellman set up the way it is with a prime and a special element G, and what makes that G special. And then if it's set up correctly, so what? Why is it okay to do this? Why is it still secure? So I'll do this in two stages because there are actually two different issues here. So for the first issue, we need to talk about primes and primitives, okay? So let's talk about why must Alice and Bob work mod a prime? Why a prime when they do Diffie-Hellman key exchange? And then how do they choose the special element G correctly? What makes some elements special and some elements not special? Okay? The easiest way to understand this is for me to show you what can go wrong when you don't follow these rules, okay? So what I'm going to focus on for the first bit here is a purposefully bad example, okay? So here comes a bad Diffie-Hellman, okay? Let's suppose that Alice and Bob chose to work mod 100, which of course is not a prime. And suppose they agreed to use special element G equals 9, which is also going to turn out not to be special. That's going to be a bad choice, okay? Then they can follow the Diffie-Hellman scheme and it will work, okay? It's still going to produce a common key. But there's going to be a security issue that is not obvious. But let's see how it works to still create a common key. So the first example here is a bad Diffie-Hellman. They choose to work mod 100 with special element 9, which isn't so special. So suppose Alice chooses her secret x to be 3, okay? Then her big A is 9 to the third, which you can work out to be 29 mod 100. So her public value of big A is 29. Meanwhile, Bob selects his secret y to be 54, and so his transmitted value of B to Alice is going to be 9 to the 54, which ends up being 61 mod 100, okay? So now Alice is going to sit down and create the key, and she gets the key by taking Bob's B, which is 61, taking her secret x, and her secret x was 3, and doing 61 cubed and getting 81, okay? Well, Bob is going to do a to the y, and a is 29, and his y was 54, so Bob does 29 to the 54th power, and he also gets 81. So look, they both created 81. They both successfully generated a common secret key. So it works, okay? Well, it does work mathematically, but that's not good enough for crypto. Just because it works, that's not a reason to use it. It turns out there is a big security issue here. Let's go through this. If you can see this, this is going to be great. It's going to help you understand why other things we do are safe, okay? So here's the deal. At the end of the day, when you do Diffie-Hellman key exchange in this situation, the key is going to be a power of 9. It's going to be a 9 to the xy, where x and y are Alice's and Bob's secrets, okay? But the point is that the key is going to be a power of 9. So the question is, well then what are all the powers of 9 when you work mod 100? Well, if you just start writing them out, 9 to the 0th is 1, 9 to the 1st is 9, 9 squared is 81, 9 cubed is 29, 9 to the 4th is 61. If you just work out all the powers of 9, what you see is eventually, watch what happens, they start to repeat. When I get down to 9 to the 10th, 9 to the 10th is 1, that's the same thing as 9 to the 0th. So 9 to the 11th is going to be 9 to the 1st, the same thing as 9. 9 to the 12th is going to be the same thing as 9 squared. They're going to start repeating in these blocks, okay? So from this point onward, everything's going to repeat in these blocks of size 10. You only get 10 different powers of 9. 1, 9, 81, 29, 61, 49, 41, 69, 21, 89, and then repeat. 1, 9, 81, 29, 61, etc. Okay? So this ends up being really bad news for Alice and Bob. Eve can use this to quickly get their key, and this is a dangerous part, without knowing their secrets. Okay? The problem is this repetitious block happened too early. So let's do it. Let me show you how. Suppose Eve sees the key exchange in example 1. All right, so let me remind you, let's keep example 1 on the screen, what example 1 was as far as the key data goes, okay? So she observes the public portion of the key exchange in example 1, but she does not know the secrets X and Y, okay? So she doesn't know that X is 3, and she has no knowledge that Y is 54, okay? Here's how Eve can get the key, even without knowing that. Well, Eve sees Bob's B. Bob's B is sent over the open line that's public. And so Eve sees that Bob says, hey, Alice, big B is 61. Okay? Eve knows that 61 is on this table because this table is too short. It's only got 10 things on it. She sees that 61 is on this table and it comes from 4. Okay? So she doesn't know Bob's Y, but Eve can guess that Y equals 4 does the same trick. The power 4 creates 61. Okay? So now Eve can compute the key in exactly the same way Bob would. So Eve would say a to the y, where a is public, that was 29. She does not know Bob's y, but she doesn't care. She will use her own y, which is 4, which did the same thing that Bob's did. And when she does 29 to the 4th, look what she gets. She gets 81, which is their key. So Eve can get the key if the table's very short, and that is bad, okay? That is bad. I want to notice one more thing here. Their key is 81. Their key is also on this table. So actually, there are only 10 different Diffie-Hellman keys here. The key in the key exchange has to be one of these 10 things before they started to repeat. So it's a big problem that Alice and Bob's key is also one of the entries in the table. There it is. It's 9 squared. It's 81. This is horrible. This is horrible. So let's get into why this is so bad, right? I'm sure that you now see that the horribleness comes from the repetition. The repetition in the blocks is too short. All right, let's think about this for a little bit. When you work mod 100, remember what Diffie-Hellman key exchange is supposed to do. It is supposed to produce a key from the set of elements 1 through 99. All right, that would make 99 different potential key options. But unfortunately, Alice and Bob's choices only led to 10 different keys, not 99 different keys, right? That's horrible. That cuts Eve's brute force work down by about 90%. That's not good, right? So certainly the absolute best version of the protocol would be one that actually led to all of those 99 options actually being options, right? In other words, that table we made should not repeat until it's gone around through the 99th power, not the 10th power, right? It repeated way too quickly. It shouldn't repeat until the 99th power, not the 10th, right? And it turns out there is a very deep piece of mathematics here that you would need to take more math classes to understand, Math 321 or 431 to work, which says this can only happen when you work mod prime, right? If you want to avoid this repetition that happens way too soon, you have to work mod prime. That's the problem with 100. You're going to get a repeat that happens too quick. All right. So that's the reason we work mod prime, is to get as many possible keys as humanly possible. Okay. All right. So when you work mod prime, right, that is mathematically the only way to guarantee your key exchange has the potential to create all the keys you would like to see in 1, 2, 3 up to p minus 1. If you don't use a prime, then Eve's brute force work is easier than it should be. Okay? Even so, with all this, it's not true that every element G is going to generate all these possible keys. All right? Only certain special elements do this, and they're called primitive elements. And that's what is special about G, is that it must be chosen to be primitive. Okay? Here's the definition. Suppose P is a prime and G is any element mod P. We call G a primitive if the powers G to the K mod P eventually generate, that's why it's called G for generate, eventually generate every single element in the list of 1, 2, 3 up to p minus 1. So you get all the possible outcomes. Okay? And it turns out, again, there is some very deep mathematics here, that when you work mod prime, primitives always exist. So they're always out there, but not everybody is. So you have to do this carefully. You know you have to work mod prime, and you know you have to use a primitive, but you have to be careful and make sure that the G that you choose really is a primitive. Okay, you got to choose it carefully. You have to check that. Okay, let's play around with primitives a little bit, and then we'll take a break. Let's work mod 7, a prime. I claim if you work mod 7 that 3 is a primitive. And so if you just map out the powers of 3 to the k, you get 3 to the 0th is 1, 3 to the 1st is 3, 3 squared is 9, but 9 is 2. You get 1, 3, 2, 6, 4, 5 at the 5th power. So look what happens. You get every element of 1 through p minus 1, which is 6. You get 1, 2, 3, 4, 5, and 6. There's 1, 2, 3, 4, 5, and 6. So you do get every possible outcome here, but not in any predictable order, right? They come out in this sort of random pattern, which is, by the way, another good security feature. The patterns are not predictable, right? And so since powers of 3 eventually map out all of 1, 2, 3, 4, 5, 6, then 3 is primitive. Okay, so 3 is primitive. If you work mod 11, I claim the element 4 is not primitive, okay? So for example, if you work mod 11, at the 5th power, you get the same thing as a 0th power. So you get a repeat here. You go 1, then 4, then 5, then 9, then 3, and then 1 again, okay? So the powers of 4 are always going to be stuck in this block of 1, 4, 5, 9, 3s. But remember, you're supposed to get everything 1 through 10. That's p minus 1 is 10. So you should get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you don't. You miss 2, for instance. You also miss what else? You miss 6, you miss 7, and you miss 8, and you miss 10. So you miss the element 2, for instance, and so 4 is not primitive. So if you work mod 11 in Diffie-Hellman, which is fine because 11 is prime, you should not use 4 because it's not primitive. So now we have the final verdict. Here is how you must set up Diffie-Hellman correctly in order to get the most out of your security. You must set up Diffie-Hellman with a prime modulus p, okay, and a primitive element g. And that's done so that all the possible keys, 1 through p minus 1, are actually achievable outcomes of the key exchange protocol. And that, therefore, makes Eve's brute force work as difficult as it possibly can be, and that's what you want. Okay? So now we understand how to set up Diffie-Hellman correctly. Once we've done that, we've still got to ask the question, well, why is it a safe thing to do? And that comes next.